All right, so now we're going to discuss the equations that we use for series and parallel circuits. First of all, for series circuits, in order to figure out the voltage for each one of these, we're going to say that, well, the loop rule says that the voltage increased by this this battery is going to be decreased by each one of these. So the voltage through each one is going to add up to the total voltage of the circuit. So whatever the total voltage of the battery, that's going to be equal to the voltage of the first one, the voltage used by the second one, the voltage used by the third one. That's our loop rule. What about the current? The current, well, since it's a series circuit, the current has to go through each one of these. So whatever current that the battery is pushing out is going to be equal to the current through each one of these. And that gives us that the total current is going to be equal to current 1 times, which equals current 2, which is going to be equal to current 3. And that's our junction rule. Because we don't have any splitting off and current is not dissipated, then that means that the current is going to be the same for all of them. Now we're going to take our voltage equation, and that's going to be equal to total voltage equals voltage 1 plus voltage 2 plus voltage 3. And we know that voltage is going to be equal to current times resistance, and we're going to plug that in for each one of these. So the total voltage is going to be equal to the total current times the total resistance, while voltage 1 is going to be equal to current 1 times resistance 1. Voltage 2 is current 2 times resistance 2, and so on. Well, something to note here is that the total current is equal to each of the currents through the resistors. So you can see that the total current here equals current 1, which equals current 2, which equals current 3. Since those are all the same, that's actually a common term or a common factor in each one of those terms, which means we can cancel it out from both sides. And what that leaves us with is that the total resistance is going to be equal to resistor 1 plus resistor 2 plus resistor 3 plus any other resistors that are in series along with the other resistors. So in order to figure out the total resistance, which sometimes that's referred to as equivalent resistance, it's going to be equal to resistance 1 plus resistor 2 plus resistor 3 all added together. So let's say, for example, I have I want 9 ohms of resistance in a circuit, but I only have 3 ohm resistors. Well, if I have 3 ohm resistors, I take 3 of them and put them in series with each other. They add up to be a total of 9 ohms. So here are our equations for series circuits, for voltage, for current, and for resistance. They're going to be equal in these respects. Next, we're going to do parallel. So what are the equations for parallel circuits? Well, first of all, for voltage, if you remember, voltage is the amount of potential energy per electron. Now, electrons can choose which path they go through, but if they go through one path, they have to use all of their potential energy. So if voltage is the amount of potential energy per electron, then that means when the total voltage here, when that electron goes through this first resistor, that means it has to give up all of its energy, all of its potential energy, because that's the only resistor it has to go through in order to get from one side of the battery to the other. So that means that the voltage across resistance 1 is going to be the same as the total voltage as it is with resistance 2 and resistance 3. All the voltages are going to be the same because the potential energy per electron, the electrons can only go down one path, so they have to distribute all of their energy in that one path. Now what about the current? Well, current, by the junction rule, the current is going to split up into separate parts. So the total current that comes out of the battery is going to be equal to the current that goes through 1, the current that goes through 2, and the current that goes through 3. So all of those currents are going to add up to be the total current of the circuit. Now we're going to use this total current equation, and we're going to find our resistance, what the equation is for resistance. Now we got V equals IR again, except this time we're going to solve for I, which is V divided by R, so the voltage divided by the resistance. So the total current is going to be equal to the total voltage divided by total resistance. The current 1 is going to be equal to voltage 1 divided by resistance 1. Current 2 is voltage 2 divided by resistance 2, and current 3 is voltage 3 divided by resistance 3. Well, if you notice up here, our total voltage is going to be equal to each of the other voltages. So that means that this voltage and this voltage and this voltage and all of them are going to be equal to each other, which means I can cancel them off. They're a common factor between the terms, and that means I can cancel them. That leaves me 1 over the total resistance. It's going to be equal to 1 over resistor 1, which is plus 1 over resistor 2 plus 1 over resistor 3. And that gives us our 3 equations that we have for our parallel circuits. This PowerPoint looks through some examples for electrical circuits. Our first electrical circuit is going to be a series circuit. And you can see that it's series because basically each resistor has to be on the same path. And if they're all on the same line, then that means they're going to be in series with each other. So in order to determine the total resistance, what we're going to do is we're simply going to add all the resistors together. In series, we add the resistors, so we get a total of 2.6 plus 1.8 plus 2.1. That gives us a total of 6.5 ohms. So that's our resistance. In order to find the current, we take the voltage and divide it by the resistance, and that's going to be 7.3 divided by 6.5, and we get a total current that's going to be equal to 1.123 amps. In order to find the power, we take the current and the voltage and we multiply them together. So we get 1.123 times 7.3, and we get the total power is going to be equal to 8.2 watts. So that gives us the total resistance, the total current, and the total power for the entire circuit for the battery right here. So the next thing I want to do is I want to determine the current, the voltage, and the power for each one of the resistors. Well, first and foremost, we know that the current is going to be the same through each of the resistors. And that's because for series, the current is the same, and the current is not created or destroyed, so the current doesn't go anywhere. It can't split off anywhere. It has no choice but to go through all three of them. So the current has to go through R1, it has to go through R2, and it has to go through R3. So the total current for each one of the resistors is 1.123 amps. Now, in order to find the voltage, we take the current and the resistance and multiply them together. So the resistance for the first one is 2.6, and multiply by the current, which is 1.123. We get a total voltage, which is 2.92 volts. In order to find the power, we take the voltage and multiply by the current. So 1.123 times 2.92, and that gives us a total of 3.29 watts. I'm sorry, 3.28 watts. So we go ahead and set those aside. The next resistor, the voltage is going to be equal to current times resistance, so it's 1.123 times 1.8, and that's going to give me 2.02 volts. The power is going to be 1.123 times 2.01, because that's current times voltage, and that gives me a total of 2.27 watts. Go ahead and put those aside. The third resistor is going to have a current which is 1.123 times resistance 2.1. That gives us a total voltage of 2.36 volts. And then the power is going to be 1.123 times 2.36, and that gives us a total power of 2.65 watts. And we go ahead and put those aside. All right, something to notice here, I want you to notice that the power for each one of these, the 3.28, the 2.27, and the 2.65, if I add all those together, that gives me a total power of 8.20, which is equal to the total power that the battery outputs. So simply put, the amount of power that each resistor uses is going to be equal to the amount of power that the battery is going to be putting out. Also notice that the 2.92 plus the 2.02, so that's a total of 4.94, and then the 2.36, so that's going to be, let's see, 2.94. That gives me a total voltage of 7.3, which is equal to the total voltage that the battery outputs. So the total voltage the battery outputs and the total voltage used by the resistors is going to be equal to each other. The next circuit, we basically have the exact same thing. We got the same voltage, which is 7.3. We got the same resistors, the 2.6, the 1.8, and the 2.1 ohms. But this time they're in parallel. And the way we know that it's in parallel is because they all have separate paths. So when they all have separate paths, that means that it's going to be a parallel circuit. Well, in order to find the resistance, we take 1 over the total resistance equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. That's going to be 1 over 2.6 plus 1 over 1.8 plus 1 over 2.1. That gives us a total of 1.416. But something to keep in mind here is that equaled 1 over the total resistance. So in order to find the total resistance, I have to take the reciprocal of both sides. So I have to take 1 over 1.416, and that gives me a total resistance of 0.706 ohms. To find the current, we take the voltage and divide it by resistance, so that gives me 7.3 divided by 0.706. That gives me a total current that is 10.34 amps. And of course the power is going to be current times voltage, so we take the current, which is 10.34 times 7.3, and we get a total power of 75.5 watts. Alright, so that gives us a total current, total resistance, and a total power for the circuit. Now I want to figure out the voltage, the current, and the power used by each one of the resistors. Well, first and foremost, we know that the voltage is going to be the same in parallel. So the voltage used by resistor 1, the voltage used by resistor 2, and the voltage used by resistor 3 is all going to be equal to the total voltage, which is 7.3. Now you may think in a circuit voltage gets used up, so how is it possible for all of the voltage to be on R1 and all of the voltage to be on R2 and all the voltage to be used on R3? Well, the logic behind it is actually the voltage is the amount of energy each electron is carrying, and electrons can't go through more than one path at once. So if the electron goes this way, it's carrying 7.3 volts. If the electron goes to the path 2, it's carrying 7.3 volts. If the electron goes to the third path, regardless of which path it goes to, it has 7.3 volts. Now that 7.3 volts is electrical potential energy. So it has to lose all of its potential energy. By the time it comes from this side of the battery to the other side of the battery, it loses all of its potential energy, just like an object that's falling to the ground. Regardless of how the object falls to the ground, the object still has the same change in potential energy. So in order to find the current, we take the voltage divided by resistance. So it's 7.3 divided by 2.6 for the first one. That gives us a total of 2.81 amps. The power is going to be the current times the voltage. So it's 2.81 times 7.3, and that gives us a total of 20.5 watts. So we'll go ahead and set those aside. For the second resistor, the voltage divided by resistance is going to be 7.3 divided by 1.8, and that gives us a total of 4.06 amps. The power is going to be 4.06, which is the current, times 7.3, which is the voltage, and multiply those together to get 29.6 watts. Let's go ahead and set those aside. For the third one, the current is going to be equal to the voltage 3 divided by current 3, so that's going to be 7.3 divided by 2.1, which is 3.48 amps. And then the power is going to be equal to the current, which is 3.48 times 7.3, which is the voltage, and that gives us 25.4 watts. All right, so we have the current and we got the power for each of the resistors, and we know the total voltage, the voltage on each one is going to be 7.3 volts. Something to notice about the power, if we take the power for each one of these resistors, the 20.5, the 29.6, and then the 25.4, we add them together, we get 75.5 watts, which is equal to the total power supplied by the battery. So the battery puts out 75.5 watts, and each resistor uses a total of 75.5 watts. Now I want to take these two resistors and put them side by side and kind of compare and contrast the likenesses and differences between the two. First of all, if you notice the resistances on the series circuit, now remember, this is the same voltage, it's the same resistors, the only difference is this is in series and this is in parallel. For series, the total resistance increases when I add on series, and that kind of makes sense. As I add more resistors on, then it increases the total resistance. However, the resistance for the parallel, notice this is 2.6 and 1.8 and 2.1, the total resistance is 0.706. The total resistance is actually less. Now, how is that possible? Well, what that does is basically each parallel path adds more paths for the electron to go. So imagine if this was the only option for the electrons to go this way. Well, there wouldn't be much flow. But if I add another path, and that means I get more flow that can flow through the circuit, which means that the effective resistance of the entire circuit decreases. You can kind of think of it this way. Maybe the 2.6 ohms is kind of like your Walmart cashier, who's kind of your old lady who loves to take forever and talk about you and your grandkids and your grandkids and wants to see all the pictures, and just takes forever in order to check out. But then the resistance 2 is kind of your guy who's been there for 10 years and just kind of hates his life and doesn't really care, wants to check you out really quick. Well, the one that's 2.6 ohms, you're going to get not as much flow through that. You're not going to get as many customers checked out, but the resistance 2 with the less the less resistance is going to get more flow. You're going to get more people that actually check out through resistor 2. But with that being said, you're still going to get people who go to this register over here, because there's still people getting checked out of here, but you're going to get more that flow through the second resistor. So essentially, you can look at each one of these as another register that's being opened in order to get people checked out in the store. So the more paths you have, the more registers you have open, the more flow you can get through, and the effective resistance is going to decrease. Now you can see the flow actually increases from series to parallel. It increases dramatically, actually. With series, it's 1.123, but in parallel, it's 10.34, and that goes back to the fact that we have more paths that we can get more flow of electricity through because it's in parallel as opposed to series. And then also we notice that the power is a lot more power is being used in the parallel circuit, because we have again more flow, which means more power is going to be used, and each resistor is going to require more of the power from the battery. And in series, we got less power, because each resistor gets the same current flowing through it with the same with a little bit of the voltage, and the voltage is going to be less. So with less voltage and less current through the series circuit, you're going to get less power being used.